will be t. So, from each of the equation, this one is from the first equation, and this is from second equation, and this one is from the last equation. Sorry, I forgot to record. All right. Okay. So let's do one simple example to illustrate the concept. First one, please find the vector equation of the line L passing through the point of 3, -2, and 4 in the direction that is parallel to the vector V, that is 2, 1, and -5. And the question will be, is the point 1, 1, 1 belongs to the line L? So how should we do this? How should we work with this problem? Remember the equation that we have. So R vector equal to R0 vector plus A times B vector. We already have one point, and that is R0. We can determine R0, and we already have B. Okay. Anyone have completed forming the equation for the line? Okay. Thanks, one. So that is correct. So this is the line in 3D. So we should have three equations. Okay. We have this equation and M. So M we can consider the R0 vector. So that a 3 OM, basically this is OM, will be 3, -2, and 4. And the vector RV will be 2, 1, and -5. So this means we have three equations. So xt will be 3 plus 2t. Okay, this is t. And yt will be -2 equal to 1 plus times t. and gt will be 4 minus 5 times t. Okay, and to find whether a point is on the line, so this means the coordinate must satisfy this equation. Okay, so this means we have three equations and we need to find t. And if the t value are the same, then we can say, the point is actually on the line. So we consider the point of 1, 1, and 1. Okay, so this means 3 plus 2 for the first equation at least. So for the first equation, so 3 plus 2t equals to 1. So this means t is minus 1. And second equation, so we have t equal to 1.5, and last equation, so t equal to minus 0.6. So three t is actually different from each other. So therefore, the point 1, 1, 1 is not on the line that we are mentioning here. Okay, anyone have problems? Oh, my mistakes. This is 3. Anyhow, 3 t's are different. Okay, so is there any problem? If not, please try another case. So to see that whether the point 2, 3, and 4 is on the line. The same example here, but instead of point 1, 1, 1, please check whether the point 2, 3, and 4 is on the line. So you can have like 3 minutes or so for this. Okay, so what is the tx, ty, and tz value for the point at least? Okay, so again, the same thing. So tx will be 2 minus 3 divided by 2, and that is minus 0.5. Ty will be 3 plus 2 divided by 1, that is 5. So tx is already different from ty. So this means that this point 2, 3, and 4 is not on the line as well. Okay. Yes. Next, let's take a look at the plane equations. Okay. So by definition, a plane is actually can be defined by two non-parallel position vectors to 2 points lying completely in that plane, r vector and r0 vector, and an orthogonal vector n, that is perpendicular to every point in the plane. So we have this equation, vector n times dot vector r minus vector r0 equal to 0, or n vector dot r vector equal to n vector dot r0 vector. Okay. And since we already know the resolution of each vector, like n vector is ABC, r vector is XYZ, r0 is X0, Y0, Z0, and r vector is a variable position vector to a point in the plane. So we can rewrite the scalar equation of the plane, okay, given, for example, given the first equation here. So we have ABC for the n vector, and r vector minus r0 vector will be x minus x0, y minus y0, and z minus z0. So this is the dot product. So we have this equation. So this means x and x, okay? So a times x minus x0 plus b times y minus y0 plus c times z minus z0 equal to 0. Okay, so this is the equation for the plane. Or if we put it in another way, we can always use this. So ax plus by plus cz plus d equal to 0. So minus ax0 minus or plus by0 plus cz0. Okay, and this one is d, the same thing. Okay. We put all this constant to a new constant. So let's work on one example to illustrate the concept. So in this example, let's find an equation for the plane that goes through the point 2, 4, and minus 1 with the normal vector n at 2, 3, and 4. So remember that we have the scalar equation for the plane. Okay, so we have a x minus x0 plus b y minus y0 plus c z minus z0. Okay, so please use that equation for the determination of ax, a, b, c. All right. So as I have mentioned before, we can use the scalar equation of the plane A times x minus x0 plus B times y minus y0 plus C times z minus z0 equal to 0. And in our example here, R0 will be the positional vector in our plane. We have the vector of 2, 4, and 1 minus 1. And the normal vector will be A, B, C. So normal vector A, B, C, that is 2, 3, and 4. Okay. So this means x0 is 2, y0 is 4, z0 is minus 1. And therefore we have the equation of 2x minus 2 plus 3 times y minus 4 plus 4 times z minus of minus 0. And this one will become plus. Okay, so we have 2x minus 2 plus 3y minus 4 plus 4z plus 1. Okay, and minus 2 times 2 minus 3 times 3, that is 12. So minus 4 minus 12 and plus 4. And therefore, we have the final equation of 2x plus 3y plus 4z equal to 12. Okay. So, because the plane that we have to go through the point of 2, 4, and minus 1. So we can test whether the point 2, 4, minus 1 is in the plane by using this equation. So 2 times 2 plus 3 times 4 and plus 4 times minus 1. Okay, so this is 4, this is 12, and this is minus 4. So this is 12, so this is correct. So this means the point 2, 4, and minus 1 is on this plane. Okay, this is a kind of double check. So to make sure that our work is okay. Sometimes it's good. Actually, it's most of the time it's good to double check our work. Okay. Is there any problem so far, everyone? Yes. The topic is not so difficult, in my opinion. Okay, if you have no problem, let's move on. All right, now we will learn about different kinds of interactions between lines and planes in 3D. So including crossing lines and piercing planes, and so on. So for the interaction between line and planes, between two or more 3D lines in space, we have four possible exclusive relationship between them. So first one will be coincident. So if line number 1 and line number 2 are in the same direction and position, okay. So let's consider. So for the first case, coincident, line 1 and line 2 are in the same direction and position. Mathematically speaking, this is true if the vector v is parallel to the vector u, and vector v is also parallel to vector ab. So we have two vectors like this, L1, two lines, L1, L2, in the same direction. And next, we have parallel if L1 and L2 are in the same direction, but different position, mathematically speaking. So this is true if V vector is parallel to U vector and V vector is not parallel to AB vector. So this is AB vector here. So coincident, this means that two lines will meet somewhere. Okay, parallel, this means two lines will never meet, basically, because they are parallel, actually. So another one, we have intersecting. So if L1 and L2 are in the same plane, okay, and L1 and L2 are in the same plane and in different directions. Okay? Mathematically speaking, this is true if the parametric equations for L1 and L2 return a unique set of solutions for their parameters value. And the last one, skew. So if L1 and L2 are in different planes and in different directions, mathematically speaking, it is true if the parametric equations for L1 and L2 yield no solution for their parameters value. So it's look complicated, but actually after the we can do some tutorial, some example, it will be easier. So for the above two cases, the angle between L1 and L2 could be found by using their dot product computation. Okay, so let's do one example to illustrate the concept. Let's say we have two lines, L1 and L2. Okay, so L1 goes through the point A, -1, 7, and -10 in the direction of the vector U, have resolution of 2, -3, and 4. And L2 goes through the point B, -6, -14, and 4 in the direction of vector V, having resolution of -3, -5, and 2. Determine if these two lines are coincident, parallel, skew, or intersecting each other. So remember the equation for the line that we have last time, and that is R vector equal to R0 vector plus T times V vector, and T is the parameter value. Okay. So let's take a look at the first equation for the line number 1. So line number 1, we have the point A, -1, 7, and -10. Therefore, xt equals to -1. Okay, in the direction of vector 2, -3, and 4. So plus 2t, yt equals to 7, minus 3t, dt is -10, plus 40. Okay, and we can do the same. So we can have the equation for line 2, and that is xs equals to -6, minus 3s. Okay, ys equals to -14, minus 5s. Lastly, zs equal to 4 plus 2s. Okay, so we have two equations. We have two set of equation for two lines L1 and L2. So after we have found the parametric equations, so next one we will determine whether they are parallel at first. So the parallel one, it will be easy. Usually the parallel one will be the easiest to determine. So if they are parallel, the directional vectors should be parallel too. So if they are not parallel, then they are also not coincident. Okay, and if they are not, they are neither parallel nor coincident, then we can set the equation and we solve for the parameter value. And if the equations resolve a solution, this means the two lines will intersect somehow. Okay, and if they are not, if we can't find any solution, then this means the two lines will be skewing, basically. So based on that, okay, and as you will see, the two vector u and v are not parallel because their directions are different. So this means L1 and L2 are not parallel and not coincident. So this means we have to determine whether the two lines L1 and L2 are intersecting or skewing. So at first we assume that L1 and L2 are intersecting. So this means there will be one point on both of the lines. Okay, one point will be the same value on both of the lines. So we will solve the equation of xt equal to xs, yt equal to ys, and zt equal to zs. Okay, so this means in this equation we will have we can find some value of s and t that satisfy the equation. So the first equation will be minus 6 minus 3s equal to minus 1 plus 2t. Second equation, we have minus 14 minus 5s equal to 7 minus 3t. And last equation, we have 4 plus 2s equal to minus 10 plus 4t. We have three equations with two unknowns, so you can pick out any two equations to solve for s and t. Okay. So by solving this, there are many different ways that you can do, basically. So, you know, you can find that t equals to 2 and s equal to minus 3. Okay. One of the simplest way is to time this equation will be to 1.5 and plus both sides together, then you can get t. And using t, you can calculate s easily. So the equation, this is equation 3, this is equation 1. So equation 3 times 1.5 plus equation 1, and you can solve for t. Okay? And you can find s easily. Okay, so for this set of equation, we can find that we can find proper value of t and s that satisfy this equation. So this means the two lines L1 and L2 intersecting each other, because we can find one value that is on both of the lines. So if you are not sure, you can put in this value back into the equation, for example. So t equals to 2. Okay, so the first equation here, we will have this is 3, and this is 1, and this is 0. And again, this one is also 3. This is 1, and this is 0. Oh, 2. The last one is 2, not 0. So this is minus 2, and last one is minus 2. The same result. Okay, so this means both of L1 and L2 will intersect this point, 3, 1, and minus 2. Okay, if we solve the setup equation, if we can't find any value of t and s, this means the two lines are skewing. Okay, is there any problem from this example? Okay. If anyone have problems, please let me know. Okay. If not, then let's move on. Okay. We can also go one step further and basically, as I've mentioned before, so we have found the solution So the lines are actually intersecting at the point 3, 1, and -2. That is the result that we have just now. Okay. So let's take a look at the relationship of line and planes next. Okay. So let's say we are given two planes, P1 and P2, and P1 is defined by the point A, XA, YA, and ZA, and the normal vector V, and that is XV, YV, and ZV. And plane number 2, P2, is defined by the point B, XB, YB, and ZB, and the normal vector U, XU, YU, and ZU. Okay. So we have three possible alternatives. First one, P1 and P2 are parallel to each other if V vector is parallel to U vector, okay, and V is not orthogonal to vector AB. So the distance between the two parallel planes is given by the projection of vector AB in the direction of vector V. Okay, so you can see the description here. This is A and B. Second case is plane P1 and P2 are coincident to each other if we have vector V is parallel to vector U and V vector is orthogonal to vector AB. Okay. And lastly, plane P1 and P2 are intersecting each other if vector V is not parallel to vector U. So these two planes will interact somehow, intersect somehow. So the procedure to determine whether if two planes are intersecting or not, and we can calculate the equation for the intersection line. So first one, we determine whether the two planes are intersecting. We need to determine the normal vector to each of the plane, V and U in this case. And then we need to find the cross product between them. Okay, remember the cross product will return a vector. Okay? So if the cross product resultant is non-zero, this means the two planes are intersecting, and we can move on to step number 2. And the resultant vector is the direction vector for the intersection. And next, we can find a point on the intersection line. So because the length of the line is infinite, so this means it bounds to cross xy, the plane xy, yz, or zx plane at some point if we extend it enough. Therefore, we can set one of the variable x, y, and z to 0 on the equation of the plane for P1 and P2, and we can solve for the remaining two variables. For example, we can set z equal to 0 and solve for x and y, or you can set x equal to 0 and solve for y and z. So we can find one point on the intersection line, and then we can write the parametric equations for the intersection line. So the parametric equation for the intersection line will be the same. We already have the directional vector V, and we can use a two vector R and R0 to form the equation. Okay. So let's try one example together so that you will understand it better. So let's say we are given two planes. P1, we have x plus y plus z equal to 1. And plane number 2, x minus 2y plus 3z equals to 1. So determine if the two planes are intersecting, and if they are, find the vector parametric equations for the intersection line L of this plane. As you can see, the two planes are obviously intersecting. So, but let's go through the procedure, the same procedure first, okay? So remember the 3D plane equation we already have. So AX plus we have AX plus BY plus CZ plus D equal to 0. ABC is the resolution of the normal vector. Okay, so this means the normal vector to plane P1 will be 1, 1, and 1. Okay, and the normal vector N2 for the plane P2 will be 1, minus 2, and 3. Okay, and we will have to find the cross product between N1 and N2. So if the cross product is non-zero, then we can say, the two planes are intersecting. Okay? And N1 cross N2 will be determinant of 1. So 1, 1 minus 2, 3 times x vector, as I've mentioned before, like this. Okay, then like this, and like this. So the last one. So 3. So the first one. Okay, so the second one. So the first one, we have this. So this means 3 plus 2. So 3 minus 2. So we have 5. Okay. The second one, 1 times 1 minus 3. So here we have, we have that. So this is 2. So minus 2y. And the last one here. So this means minus 3. So finally we get 5x minus 2y and minus 3z. Okay. This is the cross product between two normal vector N1 and N2. So therefore, this is the directional vector for the intersection line. So this means the vector W will be 5, minus 2, and minus 3. Okay? And that is first step. So the second step is to find a point on the intersection line. So as I've mentioned before, the line will extend infinitely. So this means we can find somewhere that, we can use x equal to 0 or y equal to 0 or z equal to 0 and find the other two. For example, let's say we use z equal to 0 and we solve for the other two equations. So this means we have from the previous two plane, we have x plus y. Remember, okay, so from these two equations, so we put z equal to 0. So this means we have x plus y equal to 1 and x minus 2y equals to 1. Okay, like this. So this means y will be equal to 0 and x equals to 1. So, x plus something equals to 1, x minus something equals to 1 also. So this means y equal to 0. Okay, so this means we already have one point on the line, and that is point K is located at 1, 0, 0. So according to the procedure, we already have the point and the directional vector. Okay, so we can write the parametric equations for the intersection line. So this means we can use the equation R vector equal to R0 vector plus T times V vector. Okay, and we already have the directional vector of 5, -2, and -3, and the point of 1, 0, 0 is on a vector. So this means we have the parametric form of xt equal to 1 plus 5t, yt equal to 0 minus 2t, and zt equal to 0 minus 3t. And that is the parametric equations for the line. Okay, and that's it for our example. Is there any problem from any student? Okay. If you have any problems, don't be afraid to ask me to explain one more time or so. Okay. And in the meantime, as I mentioned, you can always send me a message in team if you are feeling you are behind, and to book for additional consultation. Okay. So we have covered the relationship between lines and lines, planes and planes. So now we move on to discuss the relationship between line and planes. Okay, so between line and planes, let's say we are given a plane P1 with a normal vector x, normal vector v having resolution of xv, yv, and zv, like this. Okay, and in plane point A, xa, ya, za, okay, and we have a line L extending in the direction of the vector u, having resolution of xu, yu, and zu, passing through the point B, that is xb, yb, and zb. And as I mentioned before, the case of line and planes in general will be anywhere in 3D. Okay. So we have three possible relationships between a line and a plane. So first one, a line L is parallel to the plane P1 if the vector u of the line is orthogonal to the vector v of the plane, and the vector AB is not orthogonal to the vector v. The second condition, line is coincident to plane P1 if the vector u is orthogonal to vector v and AB vector is orthogonal to vector v. And last, the line L is intersecting the plane P1 if vector u is not orthogonal to the vector u is not orthogonal to the vector v. And in the case of the line L intersecting the plane P1, we can do more things. For example, we can find the intersection point K between the line and the plane, and the procedure to find that point K will be as follows. Because we already have the parametric equation of the line L, and it will have the form of xt equal to x0 plus at, yt equal to y0 plus bt, and zt equal to z0 plus ct. And we also have the equation for the plane P1 we have ax plus by plus cz equal plus d equal to 0. So at the intersection point, the parametric equation for the line will also have to satisfy the equation of the plane. So therefore, we can convert the plane equation to be used in terms of the parameter t, and we can solve for the t. Okay. And after that, after we have found t, then we can put the value of t to the step 3, and we can find the parametric equation for line L to find the x, y, and z coordinate of the point K based on this. So let's work on one example to illustrate the concept. Okay. All right. So let's say we are given the plane P1 having equation of x minus y plus 3z equals to 8, and the line L passing through the point A of 1, 3, and minus 1 in the direction of the vector v having resolution of 1, 1, and 2. Determine if the line L is intersecting the plane P1. If it does, find the coordinates of the intersection. So based on the first step will be we have to check whether the u vector is orthogonal to v vector. This is the first thing to check. So please perform the necessary. So in order to know whether u vector is orthogonal to v vector, what kind of operation that we need to perform? Cross product or dot product? Anyone? Oh, this is just my question to you. I haven't switched the slide yet. So the proper procedure will be we have the plane uh, we have the plane. We already know the normal vector of the plane, and we already know the direction vector of the line. So the first step is to determine whether the normal vector u of the plane is orthogonal to the direction vector v. So what kind of operation should we use? Cross product or dot product? Anyone? What should we use? Okay, dot product, that is correct. So what is the normal vector to the plane? Anyone? For the plane P1. So what is the normal vector? Actually, it's already here. Okay. So 1, minus 1, and 3. And we have the direction vector v that is 1, 1, and 2. So in order to check whether these two are orthogonal, so we have to use dot product. So can someone tell me what is the result of the dot product and vector dot v vector? Okay. For dot product, it will be easy. So just times xn plus times xv plus yn times yv plus zn times zv. Okay. So we have n is 1 minus 1 and 3, and vector v is 1, 1, 2. So therefore, the dot vector, the dot product between n and v will be 1 times 1 plus minus 1 times 1 plus 3 times 2. Okay. So that is 1 minus 1 plus 6. That is 6. So the dot product between vector n and vector v is obviously different from 0. So this means we can conclude that the line L is intersecting the plane P1. Okay. So that is the first step. If we already know the line L intersect the plane P, then next step is to find the equation that represent the parametric equation for the line L. Okay, as we already know, the line L will pass through a point 1, 3, and minus 1, and in the direction of the vector of 1, 1, 2. Therefore, x will be 1, 3, minus 1. This is the point A, and this is the vector, so 1, 1, 2. So we have xt equals to 1 plus 1 times t, yt equal to 3 plus 1 times t, and gt equal to minus 1 plus 2 times t. Okay. And we can simplify it somehow. So this means 1 plus t, 3 plus t equal minus 1 plus 2t. And we already know the plane equation for the plane P1 is like this. So x minus y plus 3z equals to 8. So we can replace this equation into this equation. Therefore, we can have this is x minus y plus 3z equals to 8. So this means we have 1 here, minus 3, minus 3, 8. So put it to the other side, we have 13. Okay. This is 1t minus t plus 3 times 2t, that is 60. So t minus t plus 60, we have 60 equal to 13. So this means t will be 13 divided by 6. Okay. So after we have found t, we can put the value of t into the parametric equations for the line L, and we can find xt, yt, and gt. That is the location of the intersecting point between the line L and the plane P1. So this means 1 plus t, okay, that is 19 divided by 6. Y equal to 3 plus t, and that is 31 over 6. And z will be minus 1 plus 2t, and that is 20 over 6. So this means the point k will be 19 over 6, 31 over 6, and 20 over 6. And that is the location of the intersection between the line and the plane. Okay. Do you have any problem for the example that I have shown just now? Just for the line and the plane intersection? Y is z. Okay. Okay, let me. Okay. Here. So z equal to -1 plus 2 times 13 over 6. Okay, so 6, this means -6 plus 2 times 13. Okay, and this is -6 plus 26 divided by 6, and that is 20 over 6. Okay, is it okay now? All right. So what part do you think is not okay? You mean the Z location? Can you speak? All right. Is there any problem until T?
So Professor, for G, it's on the calculator, it's 10 over 6, not 20 over 6. But on your way of solving it, 20 over 6. So I'm confused. Which one is it?
Okay. So we can always do the reality check, which is put everything back into the equation of the plane. Okay. All right. So now we have 19 over 6, 31 over 6, and 20 over 6. Okay. So x is 19 over 6. Okay. Minus y. Y is 31 over 6. Okay. And z for now. Okay. Let's say you use let's say we use our case, assuming it is correct. So 20 over 6. Put everything together, we have 19 minus 31 plus 60. Okay. So the first one is minus 12 plus 60 divided by 6. So this is 48 divided by 6, and that is 8. So this is correct. Okay. So the point 19 over 6, 31 over 6, and 20 over 6 is the intersection point that is correct. And you can change this one to 10. Okay, just let's say assuming this is 10, so this means this one will be 30. Okay, so 30, this means this one is also 30 here. So this one is 18. So this one is 3. So which is different from this. So this means the point that you mentioned, 19 over 6, 31 over 6, and 10 over 6 is not on this plane. Okay, so this means this point is not correct. Okay, so it's better, for the we need to always do the reality check to make sure that our calculation is sound. I think you have made some mistake somewhere, especially the equation solving, especially this equation solving. Please double check. If you need my help, just scan what you have, and I can help you to check. Is it okay now? Oh, no problem. As I've mentioned before, when we are learning, this kind of mistake is nice to know, it's nice to have, so that we fully understand the thing. Okay, so other student, do you have any problems? Don't be afraid. If you have problems, just let me know. Do you have any problem? All right. So if there's no problem, we have a few more minutes. So okay. Then let's see. So we still have a few minutes. So if you want, you can work on this simple exercise, or if you can, and if not, then we can continue this one on for our tutorial tomorrow. Remember, for our tutorial, we will change our tutorial room to the lab specialized 8.1.0001 because Dr. Clayton is injured. So he can't move very far. So we change our room. Okay. So that is opposite, very close to the Kmart, the convenience store. So it will be very easy to find. Okay. And we still have a few minutes. So if you want, you can work on this problem. So we have two planes right now. Determine whether they are parallel, intersecting, or coincident. Oh, all right. Okay. All right. So the question on assignment one is uh, is actually quite important. So now, okay. So the assignment one will be on our next tutorial, and that is Wednesday, November 9th. Okay, because usually I put that the last day, but let me change that also so that is will not cause any confusion. So I repeat, our first test will be on Wednesday next week together with our tutorial session so that student can have no problem of attending. Sometimes previously some of the students prefer to have tests on weekend or so, but that is not sometimes some students have problems to attend, for example, due to some family things and so on. So nowadays, I will choose most of the tutorial as the date and time for the assessment so that no one will have problems. Okay. Let me adjust. Oh, calculators are obviously allowed. Yes. Only computers, iPad or so, or phone are not allowed. All the written material and printed materials are allowed. Okay. You can use computer, smartphone, and iPad, and things like that. The rest are all okay. But no discussion also. Yes. Yes. All printed materials are allowed. We have like equation sheets. Ah, okay. So usually before tutorial, any tutorial, I usually have like summary, short summary or so. So you can use that as cheat sheet as well. No problem. Yeah. Let me modify the timeline first. Okay, I have modified the timeline. All right. Any mock test? Okay. So mock test usually, okay. If you wanted to, maybe tomorrow I can give you some time for, fixed time so that you know how long, how much you can. Basically, only we will have like a few questions. I haven't prepared the test yet, but tomorrow we can discuss. Okay. So this means every time I will, for every question, I will give you the allow allotted time, so you can try. Okay. The answer from Quân is correct. All right. So if you have any other question, please let me know. Please be in class tomorrow so that we can have, of course, I will provide more example for you to try at home. Oh, tutorial class. Okay. The room will be a specialized room. Actually, we will change that to the whole until the whole semester. Okay. The room is 8.1.001 next to the Kmart, next to the convenience store. So Kmart. Okay. We will change our tutorial location to that place until the end of the semester, as I mentioned, because Dr. Clyden, he had some accident, so he has to be in task, so he cannot walk very far. So the room that we have is actually just next to our office, so it take him um, not so much effort to move. Okay. All right. So I will also mention this in the announcement, so don't worry. Okay. Do you have any other question? Okay. If you have no other question, then our class today here will be concluded now. And see you tomorrow for our first tutorial, official tutorial. Okay. Yes. All right. So goodbye, everyone, and have a nice evening. Oh, we can, okay. The exercise, you can work on the tutorial question first. And after that, I can give some more exercise for you to try. Yes. Okay. Goodbye, everyone.